Hi guys, welcome back to Calculus with Mr. Robeson. Today we are taking a look at inverse functions. We're going to see when does one exist, how do we find one. Most of this should be review. We'll add in a little bit of calculus here and there, but most of this one should be review from pre-calc or before. All right, so what's the inverse? So our function is x plus 3. So what's the opposite of adding 3 to something? Well, hopefully you said subtracting 3. So the inverse function, the function that would undo adding 3 to x, would be to subtract 3 from x. All right, so now there's some properties that come about from this. If we take the inverse, apply that to x, like subtract 3, and then do the regular function back to it, like add 3, we'll end up back with the original. For instance, if we did f of f inverse of just some generic number a, well, this would be f of a minus 3, and f says we add 3, so this would be a minus 3 plus 3, which would bring us right back to a. So see how that one works? All right. It works the other way around too, so if I were to add 3 and then subtract 3, that's going to get me right back to what I started with. All right. Domain and range for inverse functions switch, because kind of we're going backwards, we're undoing what we did. Both of these would have domain and range of negative infinity to infinity, so not a big deal there, but we'll see it some more on some other guys. All right, and the points end up turning around. So if we have a point A, B, like this would be a point 1, 4 would be a point here. If we plugged in 4 here, we'd subtract 3, we'd get 1. So the points turn around. The x's and y's switch when you get to the inverse function. All right, so here's some more difficult inverse functions, and we want to show that they are inverse functions. So one way to do that is to do the composition of each other. So we could do f of g of x, and hopefully we'll get x. All right, so we're going to take g of x and we're going to plug it in here. So in other words, it's going in here for x. So we would get 2 times the cubed root of x plus 1 over 2 cubed minus 1. So now we're just going to start simplifying. The cubed root and the cube cancel each other out. So we're going to get 2 times x plus 1 over 2 minus 1. Now the 2 and the 2 cancel each other out. Times 2 divided by 2. So we're left with x plus 1 minus 1. Well, the plus 1 minus 1, they cancel, and that just leaves us with x. All right, what if we were to do this the other way around? What if we did g of f of x? Did that equal x? So now we're going to take f, and we're going to plug it in here for x. All right, so if we plug that in there, we're going to get the cube root of, now instead of x, we're going to have 2x cubed minus 1 plus 1 over 2. All right, so now we can drop the parentheses on the top. The minus 1 and the plus 1 are going to cancel. We'll get the cubed root of 2x to the third over 2. Oh, lo and behold, now the 2's can cancel. We get the cube root of x cubed, which just gives us x. So yeah, both of these work out. So that means g must be the inverse of f, and vice versa. F must be the inverse of g. All right, and this little negative 1 is our inverse notation. All right, and we could also look at their graphs and tell they were inverses, although there's a lot of stuff in the way here. Maybe I can erase some of this. Ooh, I've learned how to erase. All right, so here's G, the light gray graph. Here's F, the original, the black graph. And here's the line y equals x. And if you notice, they are mirror images of each other. So like if we kind of wrapped around this line, rotated around that line, this black graph would land right on the gray graph, and the gray graph would land right on the black graph. All right, so that's how inverse functions work. They are symmetric about the line y equals x. All right, so there are some conditions that you need to have for an inverse to exist. So first of all, the function needs to be 1 to 1. Well, what does that mean? Well, it needs to pass the horizontal line test. So remember the vertical line test for functions to see if something was a function or not? Well, when you flip over that axis, y equals x, that would be the same thing as passing the horizontal line test. So it wouldn't be a function if it doesn't pass the horizontal line test. So its inverse wouldn't be a function. So in other words, if we have a graph that looks like this, we draw a horizontal line, we cross more than once, this does not have an inverse. All right, but if we have a graph that looks, say, like this, That, anywhere we draw a horizontal line, is only going to cross once, so this will have an inverse. We might not be able to find it very easily, but it does have an inverse. All right, so some other things about this is in order to pass this horizontal line test, the function must be strictly monotonic. Mono meaning one, tonic meaning direction. As in, it's always increasing or it's always decreasing. And this is where the calculus comes in. All right, so this means the derivative has got to be greater than or equal to 0, or the derivative has always got to be less than or equal to 0 for all x. All right, so let's take a look at these two functions. Can we figure out if they have inverses? Well, one way to do it would be to look and see, is it strictly monotonic? So we could take the derivative. So this would be 3x squared plus 1. Now, does this ever equal 0? Nope, sure doesn't. If we tried to solve that, we'd get 3x squared equals negative 1. Got two negative signs there. All right, so we'd have x squared equaling a negative number. That doesn't work. So it never equals 0. And if we look at this guy, if we take x squared, ax, and square it, we're going to get something positive. Times 3, still positive. Plus 1, we're got to be greater than 0. So that means it's always increasing over its domain. So that means f has an inverse. All right, we don't know what it is, but it has one. I'm not going to try and find it for that, but it definitely has one. Let's take a look at this guy. So if we take the derivative here, we get 3x squared minus 1. Well, that is going to have a solution. It might not be pretty, but it's going to have a solution. In fact, it's got 2, plus or minus the square root of 1/3. All right, so it's going to be negative in the middle and positive on the outsides, so this is not strictly monotonic. So we could say it's not monotonic. So that means no inverse. It does not have an inverse that is a function. Its inverse would not be a function, and all we care about is guys that have functional inverses. So which one of these has an inverse over its domain? All right, so you can graph them, or you can take their derivatives and check and see what's their sign. Is it always the same sign? All right, so an easy way here is x squared. That looks like that. That's not going to pass the horizontal line test. Same with x to the 4th. It's going to end up looking like that. It's not going to pass the horizontal line test. X cubed and x to the 5th, though, they will pass the horizontal line test, or they might pass the horizontal line test. I can't tell just by looking at the equations. So now we've at least narrowed it down. So let's take a look at g prime. We'd get 3x squared minus 3. If we set that equal to 0, yep, we're going to get solutions here. So it looks like we're going to have some sign changes. What if we take a look at k? K prime is 5x to the 4th. Sure, that'll equal 0 when x equals 0, but it's going to be positive on both sides. All right, if we look at our number line, it's positive over here, it's positive over there. So that means it's always going to be increasing. I mean, it is going to have a horizontal tangent, but it's going to look something like this. Increasing, horizontal tangent, then increasing. It's going to pass the horizontal line test. This guy is going to increase, then decrease, and then increase. He's not going to pass because he's going to decrease between -1 and 1. All right, so our winner here is going to be k. Yep, there it is. All right, so how do we find an inverse function? Well, first we check, is it always increasing? Is it going to have an inverse? All right. Sometimes we can do that just by looking. This is basically the square root of x being shifted around and stuff. The square root of x looks like that. It's always increasing. So yes, it is monotonic. If you're not sure, you can take a derivative, you can graph it. It's up to you. All right. So now the actual mechanism for finding. We take this and we write it with y instead of f. So we'd say y equals the square root of 2x minus 3. And then we switch x and y. So we'd say x equals the square root of 2y minus 3. And then we're going to solve for y. Now, the reason this trick works is because this, in effect, undoes everything that gets done in the original function. So we have to undo the square root. We square both sides. We want to undo subtracting 3. We add 3 to both sides. We want to undo multiplying by 2. We divide both sides by 2. So we get that the inverse, once we get y by itself, that is the inverse function. So the inverse here is x squared plus 3 minus 2. It does everything this function does, but in reverse order. All right, so it multiplies by 2 first here, it divides by 2 last here. It subtracts 3 next, it subtracts 3 second. It takes the square root last, it squares x first. It does everything, but in the backwards order. All right, and the domain here, on the original function, let's see, the domain was 2x minus 3 has to be greater than or equal to 0, so x is greater than or equal to 3/2. The range for the original function, well, it's going to go from 0 to infinity. Right? If we plug in 3/2, we get 0, and then it keeps increasing. All right, so that's for the original function. That's for f. So that means for f inverse, they switch. So the domain here would be from 0 to infinity. All right, I know we can plug in anything there, but if we want to make it the inverse function, it's only going to be defined on this certain range here. And its range will be, well, we can write it either way, but 3/2 to infinity. That's the same thing as greater than or equal to 3/2. And there's the graphs. So here's our square root graph starting at 3/2 and increasing. And here's the inverse reflected over the line y equals x. Notice it's only being defined from 0 on forward. All right, it starts at 0 and keeps going. All right, so find the inverse of this guy on the interval from 0 to infinity. So this is its domain. All right, so the way we do that, well, we say it's y. We switch x and y. Now we're solving. We add 3. We divide by 3. We take the square root. So we get our inverse function equals the square root of x plus 3 over 3. Wait a minute, I don't see that. Let's see, can we simplify this? Sure, we can divide both things in here by 3. 3 over 3 would be 1. Hey, I see that now. Here it is. Voila. Ta-da. All right, so that is reviewing inverse functions. So that's how we find an inverse and then how we check to see if something has an inverse. All right, next time we'll bring in the calculus some more.